All right, hello everyone again. My presentation is about context utilization and the relationship to positional encodings. So in this paper, we asked the question, can calibration of positional encodings enhance long context utilization? LLMs are really good at general reasoning tasks, coding, broad questioning answers, and they're trained on a massive internet scale corpora. However, they have a certain knowledge cutoff. Knowledge is frozen after the pre-training, and that means the LLM often misses real-time data. And the trustworthiness of the LLM really depends on the source of the data. So an increasement in the grounding of real-world facts could be relevant here. This directly points us to retrieval augmented generation, or RAG for sure, which means that we retrieve domain relevant documents at inference time and injected these up-to-date informations into the prompts to ground the answers of the LLM. This, however, points to a problem that is the context length. So a typical RAG context you might think of has 10 to 50 documents, which could translate to 20 to 100,000 tokens, which might be a problem if the LLM is not utilizing the full context. However, models advertise themselves often having a context window with more than 128,000 tokens. So here, for example, we can see GPT-5 has 400,000 context window, or Grok 4 right here has 256,000 tokens. So you might think, okay, great, I can just retrieve my RAG context and put it into the prompt of the LLM. However, as current research shows, the LLM is often failing to utilize the full context as the prompt length increases. So this was first studied by Leo et al. In 2024, and the lost in the middle phenomena. Basically, what they did is take one relevant chunk that is relevant to answering the query of the user, and they placed this relevant chunk into a body of irrelevant chunks. And what they found is that when that chunk is in the beginning, there's a higher accuracy. If they place it in the middle, they get a bad accuracy. And if they place the correct answer again in the end of the document, they again get a higher accuracy again. So we can already detect a positional bias. So the aim of this paper is first to reproduce these findings and to see if these findings are still valid for modern LLMs. And the question we want to answer is also, what is the impact of the context size on these positional biases? But we not only want to analyze this, we also want to tackle these positional biases. And basically our argumentation line is that the LLMs only perceive the notion of position via the positional encodings themselves. So therefore, it should be possible to reduce the positional biases if we play around a little bit with these positional encodings. But first, we look into the reproduction results with loss in the middle, and we perform this on, for example, here, Grand 2.5, 14 billion model. This is the same needle-in-a-haystack experiment performed on the natural question answering data set. And we can see that even with a scale of only 20 answer documents, there are huge differences depending on the placement of the relevant chunk. So for example, 0.5 means that the relevant chunk is in the middle of the context, in the middle of irrelevant context. And this also becomes worse the more context we have. So for example, if we scale up to 100 chunks, we already go from in the beginning of 65%, we go down to less than 55% in accuracy. A different pattern we see in the Llama 3.18 billion model. Here we see more of a recency bias. So the closer the relevant chunk is to the query, so to the end of the context, the better the accuracy becomes. Nonetheless, we see also in this Llama model big differences. So for example, right here, if it's in the beginning of the context, we have 25% in accuracy on this task. But if we place it at a more favorable position, we already get an accuracy of more than 40%. This task, however, is fairly academic, and in real world, however, it's often not enough to just identify a single relevant chunk. We also need to reason across the whole context. And this is basically what's being done by the Babylon QA task, which basically takes the relevant info and separates them into two different chunks. And we first start off with no distractor context at all, and then slowly increase the distractor context to analyze the impact of context size and distractor content for cross-chunk reasoning. And what we see is that we have a varying scale of degradation for the two different models analyzed, and also start off with already a heavy varying baseline performance right here. But there's what we see in both models is that there's enormous degradation of performance with respect to the distractor content. So context rot is a real thing, and we need to combat this. One approach for this is the Caliope framework, which stands for Calibration of Positional Encodings. Its goal is to mitigate the positional bias without retraining the model themselves. The method basically is that we decouple the positional encodings from the actual position of the tokens themselves. So we remap the positional IDs of the LLM to basically unavoid unfavorable positions in the context. And we propose 3 different ways to do this. First one of which is the Moses calibrator, which, like Moses, divided the lake into 2 different areas. Basically, we're also dividing the sea of the tokens into 2 different positions, and basically hop over or jump over the lost in the middle zone. Basically, no chunk, so this white documents right here should be in a position where it gets lost in the middle. Second watch of which is the hourglass calibrator, which has a similar goal than the Moses calibrator, but it's basically having a smoother transition. Third one of which is the decay calibrator, and it's aimed to basically have larger gaps in the beginning and place the documents more towards the query, basically. This is in order to combat the recency bias we, for example, saw in the Llama model. So, of course, now the question becomes, how well does it perform on the data we just saw? First, we evaluate on the lost in the middle needle-in-a-haystack experiments we saw from the beginning with 100 documents in the context. And for the Llama model, we can already see that, at least in this case, all calibrators outperform identity. So what you can see here in gray basically means we're not performing any calibration of the positional encodings. We're just using the identity function. And right here, every single one outperforms, while Hourglass kind of maintains a recency bias. And for example, surprisingly, the Moses calibrator flattens the positional bias, while better than the one that the decay that actually was aimed to do so. And the Hourglass has a strong recency bias. On the other hand, we can also see that evaluation using the Gwen model, we can see that identity mostly still remains the one outperforming the calibrators. However, all calibrators besides the Hourglass stay competitive within that framework, while Hourglass really introduces some severe recency bias. We also evaluate for cross-chunk reasoning, and here the picture changes already in a certain sense. So for example, for the Llama model, we see that the decay and Hourglass, first of all, already degrade the performance. So at no distractor contact, which is somewhat surprising, and only the Moses calibrator really stays competitive, but towards the identity one, but identity already seems fairly favorable or fairly good in this context. But in the Gwen model, evaluating the Gwen model, we can also see the degradation at d equals 0. But we can see that, for example, the Moses calibrator is much better than, for example, directly using the identity, so not doing any interaction at all. And if we go to the scale of 8,000 distractor tokens, we see that actually every calibrator outperforms the identity function. So we're already getting huge gains at that scale. But a key insight from this one is that the calibration effectiveness is highly model and task dependent. So to conclude the talk, the main contributions of this paper is the investigation of Rope's role in positional biases. We performed hundreds of experiments across models, scales, and tasks, and introduced Caliope, a training-free calibration method for positional encodings in order to improve context utilization. Key findings were that loss in the middle persists in modern LLMs and intensifies with the scale of the context, and that certain calibrators improve performance for some certain model and task combinations. However, finding a task-independent improvement basically remains challenging. So these are the references right here.